Right, so today we're going to start our new topic of trigonometric equations. So this Year 12 topic extends upon our knowledge of Year 11 further trigonometry, but then puts an equal sign on the end of it and helps us understand how to solve these expressions that have now become equations. So I'm going to quickly skip past this, a review of Year 11 content. So this whole topic will be assuming that you know your compound angle formulas, your double angle formulas, your T formulas, and one of the more forgotten things is your product to sum formulas. So the first thing that we need to learn how to do in this topic is graphing the square of basic trigonometric equations. For example, if we were to graph sine squared of x. Now, there are two ways of graphing sine squared of x. The more comprehensive and, say, visual way of graphing it is by literally drawing the graph of sine of x and then just manually squaring it by visualizing what happens if I square a graph. While not impossible, it doesn't show a certain property that we're going to learn about later on in our further calculus topic about how we integrate sine squared of x, and it's through by using this particular property that I'm going to show you now. So sine squared of x, well, let's consider first up cos of 2x. It seems a bit random, but we might know that cos of 2x is cos squared of x minus sine squared of x. Now we want something for sine squared of x, so we could say that sine squared of x is equal to cos squared of x minus cos of 2x. Cos of 2x. Right. Now we know that cos squared of x is 1 minus sine squared of x. Now if we plus the sine squared x to the other side, we're going to get 2 sine squared of x is equal to 1 minus cos of 2x, which would imply that sine squared of x, if we divide both sides by 2, is a half minus a half cos of 2x. That's important. That's the property that we're going to use now to graph sine squared of x, and it's also the property we're going to use later to integrate sine squared of x. Now, to graph 1 half minus a half cos of 2x, we're going to get better at this later on, but for now I'm going to break it down into individual processes. I like to think when I'm graphing these, okay, let's start with cos of x, then look at cos of 2x, then half cos x, minus a half cos x, and then we're going to add half to that. So let's look at cos of 2x. Cos of x. Cos of x looks something like this. If that's 1 and this is minus 1, and we go down as well, come back up, and then go up like that. That is cos of x there. Okay, now let's look at cos of 2x. Now cos of 2x I've shown you before. When I put a 2 out the front, it means that there's double the amount of loop-de-loops in the same period. So instead of having 1 loop-de-loop, we've now got 2. So it's going to look something like this. So we can see that that 1 loop-de-loop here is now in a period of pi instead of 2 pi. And then it's going to be the same for this here. So we can see in the same period, I like to think like in the same time period, in the same distance, we've got 2 loop-de-loops. Okay, so that this here is cos of x, y is cos of x. This is cos of 2x. Let's graph y as a half cos of 2x. Of course, that's just going to get our amplitude and move it down by a half. I feel like I've done something wrong there. Just bear with me. So we're going to it's going to go down like that, and then up, and then down. There, that's better. And then up like that. So that is a half cos of 2x. And that would be 0.5, and this would be minus 0.5. Now we're trying to get to a half minus a half of cos of 2x. So let's find minus a half of cos of 2x. That's just going to be our original graph, and we're going to flip it upside down. So we're just getting our graph and flipping it upside down. That's all a negative does. Got to be careful here. I'm doing it a bit too fast than I should. So we want to go down there and then up and then down like that. There we go. I flipped it upside down. There we go. That is y is equal to minus a half cos of 2x. And then finally we're going to add 1 to that. Pardon me, add half to that. Now if this is minus 0.5 here, if we add a half, it means that now the minimum point of my graph is now going to be 0. So this is going to be here, and it's going to go up like this, and then down, and then up, and then down like that. There we go. There you go, and that is y is equal to a half minus a half cos of 2x. Alright, we're going to do the same with, I don't know why that said sine squared of x, we're going to do the same with cos of 2x. Now, saying cos of not 2x, cos of x squared. So we're going to graph cos of x squared. Now, same property, we're going to remember that cos of 2x is equal to cos squared of x minus sine squared of x. But this time we're going to make cos squared of x a subject. So cos squared of x, if we add the sine squared of x to the other side, is going to be, we might say sine squared of x plus cos of 2x. And then we're going to recall from our advanced knowledge that sine squared of x is 1 minus cos squared of x. And then of course we plus the cos squared x to the other side and get 2 cos squared of x is equal to 1, and this time it's plus cos of 2x, which means that cos squared of x is simply going to be dividing by 2 a half plus half cos of 2x. So cos squared of x is very similar. We can see the derivation of cos squared of x is very similar to the derivation of sine squared of x, except we've now got a plus here instead of a minus. Let's have a go at graphing that. So it's going to be very, very similar, except there's a plus here, which means there's only going to be one less step. But let's just start from the beginning. So we want to graph, first of all, cos of 2x. Oh, well, let's just start from the very beginning. A very good place to start. We'll start with graphing cos of x. So we're starting from the very basics. We might be able to do this in a few less steps, but for this example I want to do it in as many steps as possible. This is y is equal to cos of x. Now cos of 2x again is going to have the two loop-de-loops in the same period. So we're going to start here, but we're going to go down and then back up in the space of pi instead of 2 pi. There we go, so that's y is equal to cos of 2x. And then again, so we can see here that we've got one loop-de-loop here, and in the same distance we've now got two loop-de-loops. Let's do a half cos of 2x, so it's going to be the same thing, except it's going to be half as big. and then we're going to add half of that. So this is y is equal to a half cos of 2x. And let's add half to that. Again, it's going to move this lowest point of a half. This is minus 0.5 here, and this is 0.5 here. It's going to move it all up by a half, sorry. So it's going to look like this. There we go. That is y is equal to a half plus a half cos of 2x. So there we go, and that is the graph of y is equal to cos squared of x. And up here, we had the graph of y is equal to sine squared of x. And there we are. So sine squared of x, its graph looks like that. And cosine squared of x, its graph looks like that. All right, thank you.